Previously in the Waves chapter, we saw how two waves traveling in the same medium can interfere with each other and create constructive or destructive interference. When two waves with the same frequency but moving in opposite directions interfere, they create standing waves. Examples of where this can occur are waves on a guitar string. But interference can also occur with sound waves, and in fact, any type of wave can interfere. Musical instruments like woodwinds and brasses produce sound from vibrations created by standing waves as a result of interference of many waves within the air columns in the instrument. In such instruments, air can be disturbed and set to vibrate by blowing into the mouthpiece or by using a vibrating reed. The vibrations of the air can occur at many different frequencies, but most would die out except for the frequencies that are resonant with the instrument to create standing waves. It is the vibration of these waves that give the instrument their characteristic sound. The example of a standing wave used in the previous chapter was a standing wave in a string that is fixed at both ends. So the ends of the strings have nodes, or points of no vibration. The wavelength of the standing wave depends on its harmonic and is given by 2L over n, where L is the length of the string and n is the integer representing the harmonic number. The harmonic is a multiple of the fundamental frequency. For example, the third harmonic is 3 times the fundamental frequency. In the case of a string fixed at both ends, the harmonic is the number of half-wave lengths of the standing wave that can fit into the length of the string. In the animation on the screen, what is the harmonic for this standing wave? In some circumstances, such as in some musical instruments, sometimes the standing waves are not constrained at the ends, and the particles at the ends are free to move. This occurs, for example, when an air column or a tube is open at both ends. In this case, instead of having displacement nodes at the ends, we have displacement antinodes. The wavelength of such standing waves is also equal to 2L divided by n. For the first harmonic, the ends have antinodes and the center is a node. Here, the wavelength is twice the length of the tube. For the second harmonic, the standing wave has 2 nodes. So what's the wavelength of the second harmonic? For the third harmonic, the standing wave has 3 nodes. So what's the wavelength of the third harmonic? For this standing wave on the screen, what's its harmonic? And what's the wavelength for this harmonic? In some wind instruments, such as the clarinet, the instrument is open at one end and closed at the other. The standing wave set up in such a case has a displacement antinode at the open end and a displacement node at the closed end, as shown in the animation on the screen. For a standing wave with an antinode at the open end and a node at the closed end, the first harmonic of the standing wave occurs at 1/4 of the wavelength as shown in the animation. So the wavelength is 4 times the length of the tube. The next harmonic occurs at 3/4 of a wavelength. So what is the wavelength of this harmonic? The next harmonic after that occurs at 5/4 of a wavelength. So what's the wavelength of this harmonic? Thus, for a situation where the tube is closed at one end and open at the other, the wavelength for the nth harmonic can be generalized as 4 times the length of the tube divided by n, where n is an odd integer representing odd harmonics. So for these situations, there are only odd harmonics. For this standing wave on the screen, what's its harmonic? And what's its wavelength? In summary, air tubes such as a flute or a clarinet can have either both ends opened or have one end opened and the other end closed. For both open ends, a standing wave created in such a tube will have displacement antinodes at the ends. The wavelengths for the possible standing waves in such a tube is given by 2 times the length of the tube divided by n, where n is a harmonic given by a positive integer. This rule also applies for tubes closed at both ends, except that the ends will have displacement nodes instead of displacement antinodes, just like we saw with the waves on a string fixed at both ends. The frequency of that harmonic is n times the frequency of the first or the fundamental frequency. And of course, the frequency is related to the wavelength through the wave speed. For a tube closed at one end, the standing wave created in such a tube will have a displacement antinode at the opened end and a displacement node at the closed end. The wavelength for the possible standing waves in such a tube is given by 4 times the length of the tube divided by n, where n is a harmonic given by a positive odd integer. The frequency of that harmonic is also n times the frequency of the first or the fundamental harmonic.